Okay, we're going to next talk about monotone sequences. And I'll call this section 3.3. And we had actually mentioned monotone sequences previously. And so we're going to state it again more formally. And this is a definition. Let X be a sequence of real numbers. We say X is increasing if it satisfies x1 less than or equal to x2 less than or equal to x3, on and on forever and ever. x4, or let me call this xn. Again, remember, sequence is always going forever and ever. And so every element of the sequence, when you go to the next one, it's always the same or greater. Like it said, sometimes people call this a non-decreasing because you could be equal at times, many times. But in any case, they officially call this increasing. If every element is less than or equal to the previous one, then decreasing. If same idea, x1 is this time the other way around. X1 is greater than or equal to x2, greater than or equal to x3, on and on and on. People want to do it the wrong way. And like that, on and on and on. And then finally, we say X is monotone if it is either increasing or decreasing. It's monotone. So let's do a theorem. Like I said, we mentioned that briefly before. And so let's now then say the monotone convergence theorem. This is 2. monotone sequence of real numbers is convergent if and only if it is bounded. Furthermore, A if this is a bounded increasing sequence, then we can say, let's say it's something like this: the limit of that sequence is equal to the sup of the xn's, such that n is a natural number and B if x equal xn is bounded and decreasing, then the limit of xn is equal to the inf of the xn such that x is a natural number, like that. So the most important idea is that if you have a sequence that's monotone and it's bounded, then it's convergent. And again, specifically, as you can see, if the limit's going to be the sup of those bounds, and if it's a decreasing sequence, then the limit's going to be the inf of those bounds. And so if we think about this for a minute, especially the bounded, the convergent part pretty much makes sense. If we think of, say, a monotone increasing, so it's monotone increasing, then if we were to plot this up a little bit, so let's say if this is n here, and over here we have the members of the sequence. And now imagine again, if it's monotone, the members of the sequence, or it's hard to know where it starts, it could be starting somewhere. There may be some times where it's steady and that's increasing, steady, or it could be just increasing all the time. But if it's bounded, then there's going to be let's say the bound, in fact, let's say specifically, this is the soup is here. Since it's increased, you're going to say steady, and it's bounded, it has to converge because it has to kind of end up converging to something. And again, if these are all the upper bounds of the sequence, and you know what the soup is, then again, remember the soup is the least upper bound. So it's going to kind of be forced, to kind of converge to that point. If you just say it's bounded, yeah, it's bounded up here, it's going to converge. But then if you know what the soup is, it's going to have to end up converging there. And same thing, if it's monotone decreasing, pretty much the same idea. You have your X ends, maybe your ends over here. I'll put it in the picture in a minute, give you time to write everything down. So once again, if it's decreasing and it's bounded below, so to speak, you'll have a picture something like this, where this is the inf, the greatest lower bound, and it's got to converge there. And the other part of the theorem, it said it was an if and only if. So that means if you have a monotone sequence that's not bounded, it's not going to converge because it's just going to necessarily go on forever and ever, because by definition, a set would be, if it's bound, if there's a bound anywhere, then it's bounded. And so if it's monotone and it's not bounded, it has to keep increasing. Now that wouldn't be true of other sequences, of course, because you could have other sequences. Let's see. Yeah, pretty much. Yeah, pretty much. Yeah, that I shouldn't go on. That's right. So if it's monotone increasing, this was monotone decreasing. Those aren't formal proofs, but that kind of gives you just a general idea. Any questions on any of that? Any questions at all? So it's, at least when you sort of think and look at the picture, fairly logical. And let me do some more stuff here. That's probably the most important thing from that section there. And let me do a couple of other things here. I'm kind of taking the most important theorems and something we call divergence criteria. We kind of talked a little bit about this before as well. And this is maybe section 3.4. And let me do this 3.4.5 divergence. Criteria. Have a sequence of real numbers as either of the following properties. Then X is divergent. X has two convergent subsequences whose limits are not equal. Or number two, X is not bounded. The sequence is not bounded. And I probably just spoke briefly about what a subsequence is, but let me just give maybe sort of an informal definition. So a subsequence could be thought of is like a subset. And that really isn't probably a formal way to say it, is a subset of a sequence that has an infinite number of terms. That might be, that's sort of an informal way to think of it. Let me just give you some examples here. So suppose you have something like this. Maybe you have given the sequence xn. And once again, there are a lot of different ways to write sequences. And so when I'm using this xn the way I did up here, there's a lot of different ways to represent that n such that n is in the natural numbers. So it's just like, which is going to be like 1, 2, 3, 4 on forever. Some examples of subsequences might be, and sometimes you want to give this a different name. I don't know, let me call it S N, just to distinguish it. So let's say if you took 2n, would be 2, 4, 6, 8, etc. And again, there's an infinite number of choices you could have. Again, and it doesn't really have to even be systematic. You could just say you're going to somehow pick like 2, 5, 12 somehow, just as long as it goes on. If you have a way of describing it to go on forever and ever, it doesn't necessarily, like here I made it where they're even, but it doesn't necessarily have to be something that seems like a normal pattern. Or you could have like 5n, which is going to be 5, 10, 15, 20. But you get the idea that it's just again, the important thing is it's an infinite sequence. It just has to keep going on forever and ever, and it has to be like a subset.
So When we say, this is going back just a tiny bit, but when we say X is bounded or not bounded, like a sequence is bounded. Are we always referring to like the end of the sequence?
Yes.
So like, we wouldn't say like the 1, 2, 3, 4, 5, 6 just going up is bounded below, even though technically everything is above. Like 0, we wouldn't say that because.
Oh, yeah, yes, yes, you could say it's bounded below this
Oh,
one. Yes, that's right.
okay.
Yes, that's right. You could say, as long as nowhere later, it's going to go below that number. Yeah, that's right. Yeah.
But when we say bounded, we mean it's bounded above and below.
Yes,
Okay.
yes, that's right. That's right. Yeah, that's right.
Okay, gotcha.
Yeah, that's a good point. Yeah, like, yeah, in fact, let me bounded, yes, let me write that in, i.e. not not bounded above and or not bounded below. That's right. So if it's not bounded above, and when I say above, in that case, I'm talking about like as far as the value of the things are, like, no, and so therefore this would be right. It could be not bounded above, then it's not bounded. It could be not bounded below, that's not bounded. And there are even times it could be not bounded either way. Yeah, any of those cases. That's right. That's a good clarification. That's right. So for example, you could, and of course this one is not bounded. And then also along that line of thought, you could also then say, given X in, once again, the negative side as well, would be in, and then you could say that would be -1, -2, -3. That's right. So this one is unbounded because it's not bounded above. This one is unbounded because not bounded below. And just for a final thing, of course, you could even have, as you probably guessed, if you have something maybe like this, where you have maybe like -1 to the n times n for n in the natural numbers, would be what, like -1, and let's see, that'd be +2, then -3, +4. That's right. This, and then of course that one's not bounded above or below. Yeah, that's a good question. And then in that case, so these will be examples of subsequences here. And now going back also to this theorem that we had, we said that if you can have two convergent subsequences whose limit are not equal, then it's divergent. So of course, let me say here, this is divergent, this is divergent, and then so this one here, given X in, and this time we can just use the -1 part to the n. Oh, excuse me, I didn't want to do that. To the n and n. You can excuse my mess there. So this is going to be -1, 1, -1, 1, -1, 1, like this. And then you can see subsequences. Again, you can call these whatever you want. I'll say this a subsequence. Let me do one. We have, let's see, let's say 2n, such that n is in the natural numbers. So that makes the power always even, huh? And so that would give us 1, 1, 1, 1. So obviously the limit of Sn is going to be 1. And if we go the other way, at -1, these are double dots if you can't read my messy writing. And then over here, let's see, where would this, of course, it's going to always be in the naturals. And let's see, so if we have 1, so it's going to start, that'll be 1, so it's going to be negative. Those are all going to be negative. And the limit of the Tn is -1. So here we have two subsequences, and the limit of one is 1, the limit the other is 0. Excuse me, is a -1. So there we have sequence whose two subsequence converge to two different things. So they're not, it's divergent. So according to our theorem there, those are two possibilities for divergence. It's unbound. I should put this up here. These first were unbounded. Unbounded. Boy, am I messy. These two sequences were unbounded, therefore they were divergent. Down here on this one, clearly this one is bounded. It's bounded above by 1, below by -1, but yet it's divergent because we could find subsequences where the limit of the one was 1, the limit of the other was -1, two subsequences, they have two different limits, so it's divergent. Any questions on that? Okay, let me. You may have had a little bit of that in the past. This next one might be new to you, a Cauchy sequence. And for this section 3.5. And so one thing we're talking about here, again, the Cauchy criteria. Sometimes you can't find the limit of a sequence. and say it's not monotone. We can sometimes use the Cauchy criteria. To show the sequence has a limit. So again, you're trying to show the sequence has a limit, but you can't find the limit. Sometimes it's difficult to find the limit to certain sequences. And it's not monotone. Like I said before, if we knew it was monotone, then we could show if it's bounded, we would have them, even if we didn't necessarily find it, because we may or may not be able to find the soup real easily if it's monotone. But as long as we know it's bounded, we know a monotone sequence has a limit. What if it's not monotone? We can use what's called the Cauchy criteria, or talk about Cauchy sequences. And the sequence of real numbers is said to be a Cauchy sequence if for every epsilon greater than 0. Remember, before we defined the limit, we defined the limit, we had to know what the limit was ahead of time, or at least guess what it is. But now we don't have to do that. We say let epsilon be greater than 0. There exists a natural number. Remember, that sounds like what we had before. And maybe just call it HE. You can still call it N if you want. This is just a way of maybe distinguishing it from what we had before, but I think a lot of people still call this N, but that's completely up to you. Such that for all natural numbers, M and N, now that we have two of them, greater than or equal to our H, the terms XN and XM satisfy XN minus XM is less than epsilon. Again, like I said before, when we talk about limits, we always had a limit in here, what we thought the limit was going to be. We had like our XN minus our limit. But this time, see what this is saying, that let's say no matter how tiny you want to find, you pick your epsilon, you can find some natural number somewhere down the road beyond that number, such that all the elements of the sequence are very, very close together. So this is saying, you pick an epsilon And then you're going to be able to find a natural number that once you get past that natural number, all the members of the sequence are going to be real close together. They're going to be within that epsilon. That's kind of what this Cauchy criteria is saying. And so yeah, so that these keep getting closer and closer together. Again, you keep making epsilon smaller and smaller, then you just go farther down the road and find these are closer and closer together. And let me do an example how we would determine if something was a Cauchy sequence. Let's see. Show that xn equal 1 over n is a Cauchy sequence. And so much like before, we often want to do some scratch work to try to see if we can make this happen. So let's do scratch work. And so think about what we want. We would like these two to be xn minus xm less than epsilon. So we want one over n minus 1 over m to be less than epsilon. And so just like before, remember when we had like a 1 over n here when we were doing this, we had the limit over here. Kind of want to do the same thing, kind of work with this. And so let's start with that again. Let's say we have 1 over n minus 1 over m. And sometimes you're looking for easy ways of handling things. And so again, we want to eventually make this less than epsilon. And there probably are several ways to do this. Maybe a real easy way would be to say over here that since we're subtracting these two things and taking the absolute value, we can say that that's going to be less than adding them, right? And taking away the absolute value. Remembering, of course, m and n are always positive, of course. So since m and n are always positive, then these fractions are always positive. Now, if one of the fractions was negative to start with, their m and n, one of those was negative, then we couldn't say this, huh? But if they're both positive, we can say that the difference between these two numbers is going to be less than adding them together. And then now one more. So suppose, and let's also suppose n is bigger than m. So suppose that n is bigger than m, then we can say that, let's see, which way did I go here? So that means that this is going to be less than, so that means that 1 over n is less than 1 over m. So I can replace this with that, huh? I'm replacing 1 over n with 1 over m. And then, so this is going to be equal to 2 over m. And we want this to be, less than epsilon. And so much like we had before, then we can solve this. Here we can say 2 over epsilon is less than m. And then this is going to be our capital H. H, or again, if you just want to go back to using n, that's fine too. Um, or you know what I mean? This is going to be, yeah, that's going to end up being, all right. So, and let me just write it down so then you can see. So that's kind of the scratch work. Then the formal proof is let epsilon be greater than 0, choose what we have up here, n or h, whatever it is, n is equal to 2 over epsilon, put the little hat like we did before, then go through the steps 1 over n minus 1 over m. And probably in there somewhere, you know, what I probably should have done here, if you can fit it in somewhere, then we could say for n and m greater than our capital N. Sorry about that. We should fit that in there somewhere. So once you get beyond this capital N here, then this is going to be less than, or I should say, yeah, less than or equal, however you want to say it, 1 over n, 1 over m, less than 1 over m, 1 over m like this, and less than 1 over 2m. And then since m is greater than n, we can say that this is going to be less than 1 over, excuse me, I made a mistake. Yeah, I should have a 2 right here. And 2 should be here too. 2 over epsilon, which is equal to epsilon. So, and you don't have to put this last step in, you just follow the inequalities, but I just want to put this like this for all n and m greater than n. So 1 xn 1 over n is a Cauchy sequence. That. Now, one thing I did here, and they'll sometimes, if I don't know if you've ever seen the words, they'll sometimes say without the loss of generality, we'll assume that n is greater than m. If it was the other way around, you would kind of just do the same thing. It would kind of work out the same way. Instead of having 2 over m, we would have 2 over n. So sometimes when they pick one of them, and you could prove it the same either way. Sometimes they say without loss of generality, you just pick one. Because you can see if m was greater than m, we would have just done the same thing here. This would be 1 over n, 1 over n, 2 over n, then just you did it that way. So, so therefore, when you have something that'll work the same, if one is greater than the other or one is less than the other, then you can just pick one of them and you don't have to do the same proof again because it's just going to be the same steps, if that makes sense. Any question on that? Any question that at all? Okay, let's do a couple of theorems related to this. And the reason why we're interested in this. And let me actually do these kind of quickly. And let me just I'll rate this informally now. And I'll rate it more formally later. A convergence sequence is a Cauchy sequence. In other words, if it's convergent, it's Cauchy. And then 3.5.4, a Cauchy sequence is convergent. So from putting those two together, then you can simply say, and this is Cauchy convergence criteria. A sequence of real numbers is convergent if and only if it is a Cauchy sequence. And that's really the most important one of all, puts the two together, that if you have a convergent sequence, it's Cauchy. If it's a Cauchy sequence, it's convergent. And that probably going that way is the most important, that it, again, like I said, sometimes you can't find the limit, but you want to prove that it's convergent. If you can show that it's a Cauchy sequence, then it's convergent. Any question on that? Okay, we're pretty much out of time, so see you next time. Wednesday. Have a happy Monday.